Hello? Very loud. All right. So, welcome to United Astronomy Clubs of New Jersey. Once again, on site for our public presentation. So, a couple things to go over. We are live streaming this to our YouTube. So, if you ever can't make it, and I do know we have a couple people in our online audience, welcome. You can always check us out there on our YouTube. We also keep our past broadcasts there as well. You can see a list on our website of all our current and past and upcoming presentations. If you go to uacnj.org, you can also check out our socials such as Facebook, Instagram, and Twitter. Right, so couple safety things for our people here, since there are many of you, and it's supposed to be a lovely semi-clear night. I see a few clouds off in the distance. When we go to leave, we are using our headlights because we do not like getting run over, and I'm sure everyone would also like to agree with that. If we have flashlights, we are keeping them pointed towards the ground, just because even though we're using headlights, we don't need to unnecessarily blind people. If you do need the restroom, we have the porta potty to my right, your left. We also have a little museum and gift shop through the door, outlined in red, to my left and your right. We do have a couple of observatories. They are the sheds with the roll-off roofs over there that will be open for observing after the presentation. And with that, we're going to get right into our presentation tonight. Our presentation is The Great Debate in Astronomy with Max Watzky. Sorry, pronunciation is sometimes difficult. He's 17 and attends the Pingree. That's an R, right? Okay, Pingree School, and has been a member of AAI since 2018. He's given 7 talks there and manages online outreach for the club. He has an interest in research and astrophotography, and here to tell us all about the Great Debate.
Hi everyone, it's so good to be here. Tonight, I'm going to be talking about one of the most interesting episodes, at least in my opinion, of the history of astronomy. Most interesting episodes in the history of astronomy. What is now called the Great Debate. On April 26th, 1920, two giants of the field of astronomy, gentlemen by the name of Heber Curtis and a gentleman by the name of Harlow Shapley, met at the Smithsonian Institute to try to settle one of the most pressing scientific questions of the time. How big is our universe? And in order to do this, they needed to get to a controversial issue, which was, do other galaxies exist, or is it just our Milky Way? Despite its lofty ambitions, however, the debate did fail in several ways. It failed ultimately to determine whether there are other galaxies, and it even failed to approach the subject in a rigorously scientific way. However, the debate is important for us to study, particularly for aspiring scientists to study, because it not only helped lay the groundwork for our modern understanding of galaxies and the universe as a whole, but it serves as a valuable case study in the scientific method and a window into the evolving science of astronomy. So, first, let me set the scene for you. The year was 1920. The Treaty of Versailles had just been signed, ending the First World War. Prohibition had just gone into effect, although no one really listened to that. The world was still in black and white, as you can see. The Jazz Age was in full swing. And just as American society was changing very quickly at the time, so was the field of astronomy. Thanks to new technology, the field of astronomy underwent massive changes around this time, moving from a science based mostly in qualitative observation to hard quantitative data. Chief among the technological advancements that enabled this was the camera, which had come a long way since its invention in the early 1800s. By 1883, we were able to use telescopes in conjunction with these cameras to take pictures of objects in space, like this image here of the Orion Nebula taken in 1883, that showed us stars and structures that were invisible to the human eye. In addition, early photometers and spectrometers were coming on the scene, enabling us to precisely measure the amount of light coming from different astronomical objects at different wavelengths, which was an enormous help to our science. Finally, advances in optics and math helped us build the first modern telescopes, and with them, the first modern research observatories. These technological advancements helped astronomers tremendously at the turn of the century, enabling advancements like Hertzsprung and Russell's discovery that there was a relationship between the color and brightness of stars, and even the theory of general relativity, which was proven by taking measurements of stars during a solar eclipse. Thanks to this new capacity for advanced astronomical observation, we were on the verge of a breakthrough in solving one of humanity's oldest philosophical questions: what is our place in the universe? The first people to apply science to this question were the ancient Greeks before 0 AD, determining the shape and size of the Earth. But we didn't make another major advancement really until the mid 1500s with the Copernican theory that the Earth orbits around the sun. And then you might be surprised to hear this, but it wasn't until the mid 1800s that we had definitive proof that other stars were like our sun, although philosophers and scientists had discussed and theorized about it for centuries. Using the technique of parallax, we were able to finally measure the distances to those objects and determine that they were not only super far away, but also super bright. However, beyond a certain distance, parallax couldn't help us. And so there were some objects like most stars and nebulae that were beyond our reach. So by 1920, we know that we are on a spherical Earth orbiting the sun, and that the sun is one of many stars in a greater structure called the Milky Way galaxy. However, thanks to these new astronomical techniques and technologies, we were able to finally research a type of object, a peculiar type of object, which was threatening to upend this order. That object being what was then called the spiral nebula. And although we'd known about them for hundreds of years, we weren't able to really study them in depth until the turn of the century. But on the surface, these nebula appeared very similar to other kinds of nebula that we knew were in our galaxy, composed mostly of wispy filaments of gas and dust. We also noticed that they seemed to contain point sources of light as well, stars. The whole astronomical community around this time caught spiral fever. It seemed like everyone was trying to come up with some kind of theory or explanation to figure out the origin of these strange objects, which didn't fit into our categorization scheme. In general, we can divide these explanations or theories into two major camps, although this is a simplification. First, composing a slight majority, there were those who believed that the spiral nebulae were distinct galaxies separate from the Milky Way. The nexus of this style of thought was at Lick Observatory, managed by the University of California at Santa Cruz. I've highlighted that position, that spiral nebulae were distinct galaxies, in red. And then we had also Mount Wilson Observatory, another one of these sort of recently formed modern observatories, which was the center of thought for this other camp, which held that the spiral nebulae were actually like other nebula in the sense that they were part of our galaxy. And so we have these two camps, part of our galaxy and not. So between these two observatories, there was a pretty intense rivalry, at least for astronomers, going on. And it was in this tense climate that a man by the name of George Ellery Hale, something of an elder statesman of astronomy, invited representatives from both camps to speak on the subject in a formal debate setting at the Smithsonian Institute. So two men got on the same train from California to DC to represent their camps. In the red corner, Hubert Curtis, an experienced professor, lecturer, and research astronomer at Lick, who held that the spiral nebulae were not part of our galaxy, that they were in fact distinct galaxies. He was something of an old guard scientist, very conservative and skeptical of new discoveries. A man with a very reserved demeanor. He was remembered as by one of his PhD students as a small, quiet man with a remarkable sneeze. Um, on the other hand, in the blue corner, was Harlow Shapley, a much younger, much more ambitious astronomer um, from Mount Wilson Observatory who believed that spiral nebulae were part of our Milky Way. Um, and in many ways, he was Curtis's opposite, where Curtis was old, traditional, and conservative. Shapley was young and ambitious. And he was progressive too, both in his politics and in his astronomy. Perhaps this is why he sort of adopted this contrarian opinion that the spiral nebulae were part of our galaxy. He did have an ulterior motive, though. His ultimate goal was to direct the observatory at Harvard, and his primary motivation for participating in the debate was that there was going to be a representative from Harvard in the audience. So these two astronomers get off the train. They did talk to each other on the train, but they didn't talk about astronomy. They talked about Latin poetry. And they headed to the Smithsonian. Despite the name that we call it now, the Great Debate, this wasn't a true debate. Slide decks and speeches in hand, they each gave a 45-minute presentation to the audience, which is about as confrontational as you can get from astronomers, in a format pretty similar to what I'm doing tonight, actually. The transcript of this hour and a half long event came out to be 17,000 words, which we'd normally expect to take about 3 hours to read through, and so clearly there was some fudging that happened after the fact. A lot was added in. But nonetheless, this transcript is still the best tool we have to understand Curtis and Shapley's arguments, and I'll be drawing on the transcript as I break down their arguments now. So, first, Curtis, defending his view that spiral nebulae were distinct galaxies. He had 3 key pieces of evidence to support his point. The first piece of evidence that Curtis cited had to do with the prevalence of nova in the spiral nebulae, which were studied extensively by one of his colleagues at Lick, an astronomer by the name of George Ritchie. Novas are astronomical events that happen when you have 2 white dwarf stars in a binary system with each other exchanging matter, and all at once a lot of matter is transferred from one star to the other, and you have a huge flare of brightness. So this astronomer Ritchie discovered that novas in these spiral nebulae were happening a lot. We can see up in this sort of small image, in the top right corner, the spiral nebula NGC 4321. The image on the left was taken in 1901, and the other was taken in 1914. And you can see in both of them, by chance, have a nova happening in the image. They sort of appear as stars that you don't see in the other. Through a little bit of observation of a number of these different spiral nebulae, Ritchie was able to determine that the novas were happening was similar to the rate of novas in our own Milky Way. So there had to be a ton of stars, number of stars approaching the number in our Milky Way, to produce these kinds of events. The second piece of evidence that Curtis cited had to do with the spectra of these spiral nebulae. Spectra are tools that help astronomers to study the different wavelengths of light that are emitted by different objects. These different objects, which are made up of different gases, hydrogen, helium, oxygen, sulfur, etc., have different spectra with different overall shapes. So on the bottom right is the spectrum of a spiral nebula, NGC 1068, taken by the astronomer Edward Fath in 1909. It's kind of presented in a weird way, but there's 2 main components to this spectrum. In the center, you can see this. So first of all, let me say I'm sorry. On the x-axis of the spectrum is the wavelength of the light, and on the y-axis is the intensity. Although the y-axis is kind of strange in this one. So in the center, we can see this sort of broad component of the spectrum. We usually expect a kind of flat, plateauish spectrum from a star, which is emitting at all sorts of different wavelengths. And so the fact that we have this flat component indicates that there's a ton of stars in this so-called nebula. We also see these stark lines at the top and bottom of the image, which are where hydrogen, helium, oxygen, and other elements are emitting light after being ionized. And we expect to see these in more traditional nebula. And so in this larger structure, we have both stars and nebulae. Seems an awfully seems an awfully lot like our own Milky Way. Finally, Curtis supported his argument by drawing on the distribution of these spiral nebulae throughout the night sky, drawing on the work of the astronomer Roscoe Sanford, which was published in 1917. Sanford charted out the locations of all of these discovered spiral nebulae in the sky, and what he found was that they seemed to be distributed pretty randomly, um, which is interesting because with objects that are within our Milky Way, we expect um, those objects to be concentrated in the plane of the Milky Way. If it wasn't a full moon night, we might be able to see the sort of wispy plane of the Milky Way, but it's highly concentrated. Most nebula and stars that we see in our night sky are in that plane. And the fact that these objects weren't concentrated in that area seemed to indicate that they weren't part of our own galaxy. They were something else entirely. After Curtis made his argument, Shapley had the chance to rebut. Shapley's main piece of evidence in favor of his position that the spiral nebulae were part of our Milky Way was the work of a Dutch astronomer, Adrian van Manen. Van Manen had imaged the spiral nebula, spiral nebula Messier 101 over the course of several years, over the prior decade. And upon stacking all of his images together to create this picture, he noticed something peculiar. All the stars in the outer fringes of the nebula and these spiral arms seem to be rotating over time. It's a little bit difficult to see, but he highlighted the movement with arrows. So this was intriguing because if M101 was in fact a galaxy, tens of thousands of light years wide, if it was rotating this fast over the time scale of only a couple of years, it would be violating the speed of light. It would be rotating too fast. And so therefore, Shapley argued, this must not be a separate galaxy. It must be a much smaller object within our own Milky Way. This is a pretty sound line of reasoning, but the only problem was that the observations turned out to be wrong. We now know that M101 and other spiral galaxies don't rotate that fast. The observations were just faulty. It is sort of, I guess, a lesson in observational bias, I guess. When you're doing this kind of qualitative work, it's easy to let your biases get in the way and have you see what you want to see. And there's been work done recently to try to figure out exactly what went wrong with van Manen's observations. It's been a challenging problem. Curtis's second and final piece of evidence was the light curve of M31, which we now know is the Andromeda Galaxy, taken by the astronomer John Reynolds. Reynolds's photometric measurements of M31 showed that it was much brighter, sort of in the central core region, than in the outer fringes. Now, at the time, the bright core of our own galaxy wasn't well understood. And so it was just assumed that the distribution of stars in our galaxy and in any hypothetical galaxy would be uniform throughout. Therefore, Shapley argued M31 didn't resemble our galaxy and was instead some single bright point source of light, probably a star, surrounded by lanes of dust. A pretty shaky argument, if you ask me, but he couldn't really have known better. So, with both men having made their arguments, the nice discussion ended. There was tea time, and then everyone went home. If you're curious about what happened to our debaters afterwards, Shapley did get the job at Harvard, and he eventually got his face on the cover of Time magazine up in the top right. I'm not sure what he's looking at in that picture. Curtis, on the other hand, would go on to construct and direct several observatories of his own. On the topic of Curtis, the audience was won over by his reasoning. That these spiral nebulae weren't part of our galaxy, that they were distinct galaxies, and he did turn out to be right in the end. But I don't really think it's fair to consider him a winner, or Shapley a loser, really. Both men relied on qualitative, openly interpretable evidence to support their arguments. And even though Curtis turned out to be right in the end, he failed to conclusively settle the issue through hard data. However, it didn't take very long for this conclusive solution to come along. In 1925, the up and coming astronomer Edwin Hubble objectively determined that these spiral nebulae were in fact separate galaxies by measuring the distances to them. He was able to accomplish this through the use of a cosmic yardstick of sorts, a special kind of star known as a Cepheid variable. So Cepheids, of course, are variable stars, which means that their brightness changes over time. On the left, I have a graph showing the brightness of a variable star called Kappa Pavonis taken with a space telescope. This is modern data. And we can see that the brightness changes periodically over the course of about 7 days. I think, yeah, it's the order of magnitude is about 2.5 times. So at certain times, this star is around 2.5 times brighter than at others. Pretty incredible. Um, a lot of stars are variable, though, but Cepheids are special. In 1912, one of the female astronomers at Harvard, Henrietta Swan-Leavitt, discovered that there was a direct correlation between the absolute brightnesses of these Cepheid variable stars, which is shown on the y-axis of that graph on the right, and the period of these stars, so how long it took between these peaks of brightness. This is so the brighter that these stars are at the source, their absolute magnitudes, the longer it takes for them to pulsate. And this is useful because if you know how bright an object is at the source, how much energy it's actually putting out, and you're able to observe using a telescope and a photometer how much of that light is actually reaching us, you would be able to determine the distance to that object. So Hubble applied Leavitt's work to the study of spiral nebulae by measuring the pulsation periods and brightnesses of Cepheid variables in several of these spiral nebulae. And what he discovered was revolutionary, really. So here we see Hubble's data for M31 again, the Andromeda Galaxy. In the second column here, we have the period that he observed of a number of Cepheid variable stars. And on the far right is the photographic magnitude that he observed of the stars. So how much light is actually reaching us. So it's interesting because we have very, very long pulsation periods here. What Leavitt determined was that the longer the pulsation period was, the brighter the star at its source, and so these stars must be extremely bright at the source. They must be outputting a ton of light. The only problem is that these photographic magnitudes, how much light is actually reaching us, are super dim. The magnitudes there are reported as 18 or 19. So these stars are thousands of times dimmer than the stars that we can see with our naked eye. The only possible explanation is that these stars and M31 as a whole were extremely far away, much further than the extent of the Milky Way, for the light from these super bright stars to become so dim. I wasn't able to find a graphic with Hubble's own calculations, so I ended up recalculating using his data the absolute brightnesses of the Cepheid variables that Hubble observed, and then from there the distances. My number for the distance to the galaxy came out to around 1.8 million light years. Hubble's was a little bit larger, and so was the modern estimate. For comparison, though, the Milky Way is now understood to only be around 50,000 light years in diameter. Sorry, not in diameter, in radius, from center to edge. Overnight, so the universe had grown from 50,000 light years to 2 million, a factor of 50. When Harlow Shapley received the letter from Hubble detailing this result, he very famously said, "This is the letter that has destroyed my universe." And so with this discovery, with this revolution really, would come an entire new era of astronomy, of galactic astronomy. But that's a story for another Saturday night. Thank you so much. I'll be taking any questions.
All right. Thank you so much, Max. Hold on. Thank you. I didn't want to trip over the cord. All right. So, before we get into questions and answers, because I do know there was at least one question on an online chat. For those of you who got here during the presentation, if you need the restroom, we got the restroom to my right, your left. We do have a gift shop and museum area through the door to my left, your right. Um, when you ask a question, and I call for a question, keep your hand up until I get to you, and do wait till I hand you the mic, because chances are, if you have a question, our online audience also has the same question and might be a little too shy to speak up, or we get good questions bouncing off of that. Um, that being said, we're going to start with the first question that I saw online. And is there a chance that the observations were less faulty and more doctored, referring to Shapley's observations?
So I'm assuming that's about the this
Yeah.
galaxy here.
Uh,
Or
during the presentation, I believe you mentioned that um, his observations that led to his conclusion were faulty,
yes.
or that he, and is it a chance that, oh, I misinterpreted it, and more of, oh, I purposely skewed the data?
So it's a little bit unclear. I was actually reading a paper very recently on what could have caused this error, and the consensus now is that Van Manen was removing the camera from his telescope between each of his exposures if it didn't come out well. Um, and so there could have been some kind of skewing that happened there with his measurements of exactly where all these stars were. Um, I don't think he would have purposefully screwed with his measurements, and even if he didn't, I'm reasonably sure that Shapley wouldn't have misconstrued the data in that way intentionally. But there is a possibility, I guess.
All right. Is there a question from our audience out here? Ooh, we got one.
Quick question about the HR diagram, because a lot of what we know
Yes.
about HR diagrams, the modern version, do you have a copy, or have you seen, because some of the supernova remnants and data uh, some of those other things would show up on a modern HR diagram, but obviously they didn't know about that then.
Mm.
So I'm interested in a historical HR diagram, whether it looks significantly different from the one we have now.
I'm not really sure. Um, I haven't looked into HR diagrams too much. Um, and for those who don't know, those are the um very famous diagrams that show the color of stars plotted against their brightnesses, how bright they are at the source, that absolute magnitude. Um, but I wasn't actually aware that there was a major change in that. You might have to tell me more about that actually.
That would probably be a good thing to look up online, Paul. And sounds like a great future addition to the presentation.
Yeah, absolutely.
All right. Is there another question? Anyone? I hear the cicadas screaming. It's that time of year where the trees all decide to scream. Really? So, I actually have a question. How did you get into astronomy?
How did I get into astronomy? So, my dad showed me a lot of Neil deGrasse Tyson documentaries when I was like 7 or 8. Um, but I never like pursued it much in any meaningful way until I joined AAI in Cranford a few years ago. A friend took me there. She wanted to go for her birthday. Um, and I ended up getting really into it. She never went back. Um, uh, and that community was sort of how I got into it. They were super supporting. They let me do talks, like from the very beginning when I was like 14. Um, it was a great community, and that's sort of how I got into it.
Right. Is there Paul again?
Max, if you could you turn back to the to Hubble's data?
Absolutely.
And maybe you could help me understand maybe the relationship to uh, what, first of all, magnitude is, and why the
Yes.
number seems to be going up when it's dimmer.
Yes.
And also maybe you could help me understand the relationship between a source of light and the
Sure.
and its distance from us.
So, magnitude is sort of an arbitrary way of measuring the brightnesses of things. It's logarithmic, so each increase of 1 in magnitude corresponds to an object being 2.5 times dimmer. Um, and it's sort of reversed from what you'd expect. So if you see something that's very negative or very low in magnitude, those are brighter objects. And if you see something that's very high in magnitude, like 18 or 19, that's a very dim object. As for the relationship between absolute and apparent magnitude, absolute magnitude is a measure roughly of how much energy a star is outputting, or really anything is outputting in the form of light. Um, the official definition is how bright something would appear if it was at a standard distance from us. I think it's 1 parsec. But really, we can use it here as a proxy for how intrinsically bright the thing is. And then the apparent brightness or magnitude is how bright we actually perceive it from here on Earth. So taking that car's headlights, for example, the closer that car gets to us, the brighter the headlights appear. And the closer a star is to us, the brighter it appears, regardless of its intrinsic brightness. And so if you know how bright something actually appears and how bright it intrinsically is, you can make a stab at the distance to that thing.
Ooh, I got a follow-up question actually for that. For reference, what is the magnitude of the sun and then the second brightest star in the sky? I'm assuming he's
Oh,
saying
God.
that because the
A
sun's
test.
the first brightest.
So I'm pretty sure Vega is pegged to a magnitude of 0. I think the sun is I couldn't even tell you, a magnitude of like -15 or something like that. And then the brightest stars in our sky are around, I think, -1 or so. A negative a few.
Yeah, the problem with starting to determine magnitude before we had all the data, I believe, is the main problem there, because I believe they started trying to determine magnitude back in like ancient
Yes.
Greece.
So that's how it got started. It was ancient Greek astronomers who devised the magnitude system, and we've all just sort of been stuck with it for the last 2,500 years, even though it doesn't make a ton of sense.
At
But yeah,
least
they
everyone
they
already knows it.
yeah, but they did all they pegged Vega to 0 and then figured out the magnitudes of a couple other stars by eye. Um,
All right. Was there another question from our in-person audience? Ooh, we got another one.
So, since then, the great debate was whether there's one galaxy or many galaxies.
mhm.
Now that we know there's many galaxies, so do you believe in the multiverse or do you
Multiverse.
believe in the universe?
Um, that's a little bit beyond my pay grade. But it's a super interesting question. From an astronomer's perspective, we don't see a multiverse. But there's all sorts of like interesting physics ideas now, about branching universes and things like that, and it's definitely a possibility.
Falls under the definition of more data currently available is inconclusive. All right. Another. Oh, they said they didn't realize the magnitude levels were actually from so far back. So the next question I got for you is, if you could meet any one person from history regarding astronomy, who would it be?
That's tough actually.
There's so many.
Yeah. In learning for this project, honestly, I'd love to meet any of the people who were involved in this. I was a little bit hard on Curtis and Shapley, but they sort of had to work with what they had. Um, Hubble. Oh, you guys don't need that. Uh, Meeting Hubble would be incredible, though, I think.
Good choice. Anyone else with a question? I hear crickets. They are very loud. All right. So it looks like we've kind of exhausted the questions. I'm just going to give it a couple minutes because unfortunately stream delay is a thing where by the time I say something, it takes a minute for our online audience to actually hear if they have any last minute questions. So again, I want to thank you all for coming out and joining us on this night. I want to thank our online audience for also joining us. And I especially want to thank you, Max, for coming out. And I'm definitely going to try and get you scheduled for another couple of talks here.
Absolutely. Thank you so much
So-
for having me.
With that, it looks like our questions have dried up, and I wish you all a fun night. Like I said, we do have a couple of observatories open with telescopes. Do be mindful of the cars, and when you do hop in your car to go home, again, use the headlights because we like living.